Isotopes! A Science production. So what is an isotope? An isotope is two or more forms of the same element that contain equal numbers of protons. If they have equal numbers of protons, that means that the same element. Protons give you the identity of the element. But different numbers of neutrons. And hence, hence differ in relative atomic mass but not in chemical properties. Since the proton number is the same, they have the same chemical properties. It's the same element. But since the number of neutrons is different, now they have different masses because neutrons, in addition to holding together protons, have a mass of 1 atomic mass unit. So if you have more or less of them than another one, it must be heavier or lighter in terms of mass than the other one. A good analogy would be two astronauts famous for doing twins experiments, one in space, one at home, the Kellys. They're identical twins. So kind of like two elements that are the same. They have the same number of protons, except one of them might be a little bit more massive than the other. Not going to say which one. But it doesn't always have to be pairs. It could also be 3 isotopes of an atom. It could also be 4, 5, 6, 7 different versions of the same element, but all 7 or 5 or 3 might have different numbers of neutrons, so they have a different relative mass. Now, how do we notate different isotopes? We have to be able to describe them differently if there's more than one kind. So, since they're the same except for the mass, we need to show this with either a symbolic, like their nuclide notation, or we can do it in written form. Here are 2 examples with chlorine. You would read this as chlorine-35, both in the symbolic notation and in the written notation. For the symbol, we have chlorine, the element symbol, and in the top left we have the mass number, which is the number of things in the nucleus that are contributing to its mass. 35 things in the nucleus, protons and neutrons together. We don't need to read out loud the atomic number because if it's chlorine, it's only ever allowed to have atomic number 17. So anybody with a periodic table could look that up anyway. In the written form, again, chlorine tells us, if we had access to a periodic table, everything about its proton number. So we just need to have the hyphen. The hyphen is important. It's not a minus. Chlorine, hyphen, then the mass number of 35. You read them both as chlorine-35. Now, why are there different isotopes? Well, the neutron's role in the nucleus is to hold together the protons. I said that previously. And more than one arrangement can hold the nucleus together. You can have more neutrons and still hold a nucleus together. You can have less neutrons and still hold a nucleus together. It's kind of like a person who follows a recipe for baking cookies and somebody who just does it by eye. They're still going to be very good cookies within a certain reasonable amount. They'll still be held together. So, some arrangements are only stable for a while. For instance, there are 3 different isotopes known to exist for carbon. There's carbon-12, which is 98.9% of all the carbon in the universe is carbon-12. It has 6 protons, because again, it's carbon, so it has to have 6 protons, and 6 neutrons. 6 protons and 6 neutrons in the nucleus added together means it's got a mass of 12. That's why it's called carbon-12. There's also carbon-13. It's rarer. Only 1.1% of all carbon is carbon-13. It has 6 protons and 7 neutrons. 6 plus 7 is 13, gives us the mass number for carbon-13. Then carbon-14 is even the rarest of them all. It's radioactive. It's less than 0.1%, so not less than 1%, less than 0.1% of all carbon is carbon-14, and it's got 8 neutrons. What do I mean by stable isotopes? Are all isotopes stable or are all isotopes unstable? Well, here's the trick. There's both stable and unstable isotopes. Isotopes just means it's a different form with a different number of neutrons. Some of those different forms can be unstable. Stable isotopes don't decay, meaning the nucleus in the center is fine and it's not so catawampus and wobbly that it doesn't need to kick stuff out of it, as such as radioactive decay or releasing radiation, particles, or energy to stabilize itself. Unstable isotopes will eventually decay, and they are called radioactive, or radioactive isotopes, also referred to as radioisotopes. Percent abundance, okay? I talked about their abundance in nature, or how they're found, or their percentages. Well, what does that mean? What is its importance? Well, some isotopes are more common and stable than others. Scientists have recorded their abundance in nature, and you can see an example here with lithium-6 and lithium-7. About 92% of all lithium is lithium-7, with a mass of 7, which means it's got 3 protons and 4 neutrons. There's also lithium-6. It makes up about 8% of all lithium, which means it's got 3 protons and 3 neutrons. You can see another example here with oxygen. Oxygen-16, oxygen-17, and oxygen-18. You can see that they have their mass numbers, but also have their more accurate mass, their absolute mass. So oxygen-16 has an absolute mass of 15.994915 atomic mass units. Okay, that's the units we use to describe something as small as subatomic particles. And it has a percent abundance in nature of 99.757% of all oxygen-16. Of all oxygen is oxygen-16. Then there's the percentages 0.038 for 17 and 0.205% for 18. Now, what does this mean? Well, scientists are always trying to give you information on the periodic table as to what most likely you're going to encounter in nature, or most often. Let's say that you had a bag of 100 atoms of oxygen. You stuck your hand in there and you were only able to pull out 1 atom of oxygen. Which isotope of oxygen do you think you're most likely to pull out? If you're thinking it's the most abundant, yeah, the one with 99.75%, okay, that's the most abundant one. That means over 99% of all the atoms in the bag would be that one. So if you were to reach in there randomly and pull out one, it's most likely going to be oxygen-16. Now, how are we supposed to get an average mass? I've been told that there's average masses on the periodic table. Well, a traditional average does not reflect percent abundance in nature, and percent abundance in nature is important. So if we look at that example for oxygen again, and we did a traditional average, and we just added up those masses, we would end up with 50.993 atomic mass units, and then we would divide by 3, like a traditional average, and we would get an absolute average of 16.998 atomic mass units. The problem with this is that we already identified that the most abundant, the one that you're most likely going to encounter, is 15.995 atomic mass units, oxygen-16. This one resembles oxygen-17 more closely. So it's not a good way to reflect the average of all the isotopes. So we're not going to use this. Well, how did they get this 15.999 atomic mass unit average on the periodic table that most periodic tables show? Where did this come from? Well, what they did is they used a weighted average. I'm going to talk about that in a moment. What is a weighted average? Here's how you calculate it. You multiply the most accurate mass available, so 15.995 atomic mass units, by the percent abundance, but it has to be converted to a decimal. Now, it says most accurate mass available. If you didn't have the absolute mass of the isotope for oxygen-16, the only mass available is that 16 that you see in the upper left-hand corner. But if they give you the most accurate mass, that's the one that you should be using. So we need to convert this 99.757% to a decimal. We convert this to a decimal by moving the decimal places 2 places to the left, or multiplying by 100. Now here's where a lot of people make mistakes, and I really hope that you don't fall into this category. Always move the decimal 2 places to the left or divide by 100. Do not just move the decimal to the front of the numbers thinking that that converts it to a decimal. We need to convert it to its equivalent as a decimal. So each one of the isotopes of oxygen has been converted from percent to decimal below. You can see that at 99.757% turns into 0.99757. 0.038% turns into 0.00038, and 0.205% turns into 0.00205. What we do is we take each one of these masses and we multiply it by its percent abundance as a decimal, and we get each one of these products as its contribution. What are we supposed to do with these products? We add them. There is no division in a weighted average. You multiply the mass by its percent abundance in nature as a decimal, and then you just add up all those contributors. When you add this up, you get 15.9995 atomic mass units. So on a number scale, if we're looking at the three different isotopes of oxygen 16, 17, and 18, our average falls in right there, right before oxygen 16, which is what it's supposed to be. That's the most abundant one. So it skews the results to reflect the one that's most abundant in nature. Average mass number versus mass number. I thought they were the same thing. Aha, they're not. So huge difference between these two terms. Okay? One is a description of the number of subatomic particles in the nucleus, and it's always a whole number. That's your mass number. The other one is a weighted average of the different isotopes' masses, what we just figured out how to calculate. So average mass is sometimes referred to as isotopic mass, average atomic mass, or atomic mass. The one thing it is never referred to is mass number. Mass number, since it's a number, is a whole number, and it's a description of the number of things in the nucleus. Now, some elements do not have a decimal number as their average mass. Can you think why this might occur? Let's take a look at the periodic table a little bit closer as to which ones don't. Looking down here, you can see seaborgium. Seaborgium has got an average mass or atomic mass of 266 AMU. How can it just be a whole number? Can you think of a reason? The reason is there's no other isotope known to exist of seaborgium. Okay? There's only one, so when you take its weighted average of no other isotope to multiply percent abundance, 100% of seaborgium is considered to be seaborgium 266. So the reason being is it's radioactive. Most of the radioactive elements are already unstable and will readily decay into something else. So if it's already unstable, there really is not much of a chance for there to be a different version of it with a different number of neutrons, because then it would be ultra, ultra, ultra unstable. We would never measure it, or it wouldn't exist as an element. Thanks for watching.